everybody. Great to see you today. We are pretty much ready to get started. Today is hands-on if you would like it to be, so it's meant to be a fun little workshop together. If it gets you excited, you can move up closer and hang out with us up here and get to stare at our gorgeous faces. So feel free to move up. And today, we're really thrilled to be talking with you about a very exciting new capability in Earth Engine that Justin has had a huge hand in creating and making possible. So we're just thrilled to get to share it with you all today and to see what you do with it. So with that, we'll get started. We're going to start today with some brief introductions. Then we'll discuss how you might link together 50 years of Landsat Imagery, as promised by the title. And then we'll get into the hands-on workshop or demo. So if you're comfortable in Earth Engine and you're excited to be hands-on today, today's a workshop for you. You can follow along with us in your own script, and we'll provide that template. If you're new to Earth Engine and you're here to see what's possible, that's great. Just follow along as a demo. You can sit back, relax. It's been a long week. No problem with that. So we'll start with introducing ourselves. Justin?
Hi, I'm Justin Broughton, Developer Relations on the Earth Engine team. And this is super exciting for me. Annie and I met at Geo for Good in 2019, the last time that it was in person. And I was doing office hours, and Annie came by and was asking about MSS imagery, Landsat imagery from the 70s. And I lit up. This is something that's been a big interest of mine since about 2012. Yeah, it's been this sort of hobby to try to incorporate MSS into the Landsat time series, and so I had lots to say about it, and had this process I was calling LandsatLinkr, and over the last couple of years, Annie and I have been working together a little bit to make some improvements on the workflow, and so it's exciting to be back here for the, the most recent in-person event, sharing some of the things that we had talked about a couple of years ago. Feels very full circle.
Yes, and Justin's being very humble. He's written LandsatLinkr from start to finish, and so I'm mostly its spokesperson, and I'm here to get you excited about it today and talk you through it, but huge thanks to Justin for making this possible. I couldn't be more excited. So I'm Annie Taylor. I'm a PhD candidate at UC Berkeley, and I'm using Earth Engine and other geospatial tools to study the ecological impacts of indigenous stewardship, and I'm partnering with the Amamutsan Tribal Band, which is a local indigenous community, to this area. I've also worked with a number of environmental organizations as a GIS analyst, and my favorite thing to do is lead Earth Engine workshops, so I'm really thrilled to be here today. In fact, today's workshop is going to take us to a part of Amamutsan homelands. So the Amamutsan Tribal Band's homelands are south of San Francisco Bay and east of Monterey Bay, and they founded a land trust which works to steward the lands that are shown in this map on the right. So if you're joining us in person today, which many of you are, we are just north of this area on the map. And the tribe and land trust are doing incredible work to both protect their sacred sites and steward the many ecosystems that are found in that area. So I've popped some links here on the slide for you to check out, and I hope you support them if you can. This photo on the right is a photo of tribal members helping to conduct a cultural burn in a part of this area that we'll be looking at today in partnership with a state agency. So it's incredible work. Please check them out. So what is LandsatLinkr? If you hear, you might know that Landsat represents our longest continuous view of the Earth. It has been imaging the Earth's surface from 1972 to the present. And so today that means we have 50 years or a half century of Landsat imagery, which is a great milestone to celebrate. But across those 50 years, Landsat has made use of 5 different sensors: MSS, TM, ETM, OLI, and now with Landsat 9, OLI-2 launched on that satellite. So it's a lot of different sensors that vary in their design and quality, and linking them together for a full 50-year view is actually really quite challenging. So I don't know if you're looking at the literature, you've seen a lot of research that analyzes Landsat time series from 1984 to the present. And today we are talking about how to include those mysterious prior 12 years that were solely captured by the MSS, or multispectral scanner sensor. So very exciting new development to talk about. As you can imagine, this process is very complicated. So the workflow has evolved since this figure on the left was created, but it gives you a sense of how many steps are involved. And so I hope you're experiencing some appreciation for Justin right now, because he's scripted many of these processing steps for us in the Earth Engine Python API. So it's made easier for us. It's made possible. The brief workflow of LandsatLinkr is that it's assembling all of the image collections across the 5 satellites that carried the MSS sensor. It's calculating top of atmosphere reflectance, it's using some different quality filters, and it's also applying an MSS-specific cloud mask. Then the user, us, is able to filter through the remaining MSS images and filter out images with things like major scanline issues or other noise that we don't want to see in our time series. So there is a step that's very interactive and involves you as a spatial scientist, and so that'll be probably the hardest part of the workflow. It's then using those remaining MSS images to create pseudo-TM imagery using the overlapping MSS and TM images. So there are a few satellites that carried both sensors, and so we have these coincident image pairs that are used to build that relationship. Those pseudo-TM images are then linked together with the rest of the Landsat archive that you're probably familiar with to create that full 50-year view that we get to see today. So these figures in the center and the right give you a sense of how those overlapping images are used to create that relationship. So the 1970s are important. LandsatLinkr is very exciting. Many of us would love to use MSS data in our analyses and look at those mysterious 12 years, but the process of harmonizing MSS imagery to the rest of the archive really impedes us from including it, and I am in that category. But with LandsatLinkr, all Earth Engine users can now access that MSS imagery, harmonize it, and take that full 50-year view of your study area, your system that you're studying. So we hope it really empowers you to use a lot of these data that have been unanalyzed so far. This image that you're seeing is of Mount St. Helens near Washington, and the parts that are highlighted in color are showing you big changes that occurred just in that 12-year period. So this is an example of the type of information that we would be missing when we don't include MSS imagery. It's trying to get you to learn that it's worth it to go through the workflow. So there are some things to consider before working with MSS imagery, and you might already be familiar with these. I was not when I approached Justin, so we'll provide a quick overview of those differences. MSS imagery has fewer bands, has coarser spatial resolution, and also has lower radiometric resolution as compared to the TM sensor and the sensors that came after it. So I'll talk more about what each of those mean, but briefly you should know that LandsatLinkr is synthesizing, resampling, and stretching the MSS data to match the TM data. So it's really built to be used with time series visualization or major disturbance detection, but those quantitative values are not as suited for detecting subtle ecological changes. So you can assess whether MSS data is right for your study question. This figure is showing you how those 4 bands of MSS data compare to the other sensors that came after it. So you can see it's very limited in its spectral resolution. And what do we mean by radiometric resolution? So this figure is showing you the radiometric resolution, the number of shades that are distinguished in the MSS imagery on the left and the TM imagery on the right. So you can see we're essentially able to see fewer shades of color or reflectance in that image. And we think it's cool that this figure also happens to show you their difference in spatial resolution. So you can see that the 60-meter MSS pixels each contain 4 TM pixels. So they have that coarser spatial resolution as well. Lastly, MSS coverage of the globe is not even. So this map is showing you the total number of MSS images that were captured globally within that whole 12-year period. So you can see it's quite sparse in some areas of the globe. So if your study area has lower MSS coverage, you might still have gaps in your time series, or you might need to be loosening your filter requirements as you run through LandsatLinkr. So these are just sort of the caveats to consider. So as we mentioned, LandsatLinkr is an imperfect process. It's synthesizing and stretching that MSS data, and the annual composites that are produced by the workflow are really meant to be run through LandTrendr. LandTrendr is a temporal segmentation algorithm that's going to take all of those messy annual values and fit them to a linear piecewise function that's creating these linear trends that you and I, as ecologists or scientists, can more easily interpret. And it's doing this for each pixel individually. So really powerful algorithm. Today is not a LandTrendr workshop, but many amazing LandTrendr workshops and guides exist, and we have linked those in the worksheet so that you can learn more as you dive in. This is one of the outputs that we can create with that fitted linear time series, and this is a map near Western Oregon showing you the year of the greatest disturbance in that area across that color ramp. So you can see more recent years and more years in the past. This is a really cool visualization, and many other great views of change and disturbance over time are possible with LandTrendr. So we're almost ready to dive into the workshop. This is to get you excited. This is what we're creating today together. It's an animation of 50 years of fitted, highly harmonized Landsat imagery. So this is really the result that we will get to make today, and that you'll get to make for your study area moving forward. I love this image. If you're from this area, you can see the CZU fire burn through the redwoods in the lower left of the map. You can see crop rotations happening in the Central Valley of California to the east. And if you know where Henry Coe State Park is, kind of in the middle, you can see wildfires burn through that area very frequently. So it's giving this really cool view of our local area here. So I'm just going to mention a few more things about the workshop format before we dive in and lose the slides. I'll be taking us through the workflow. We're going to start in a Colab notebook and run through all the processing steps in the Colab notebook. We'll then hop over to the code editor, where we will visualize those results and investigate any issues, because there might be. We've talked you through the caveats of MSS imagery. It's not perfect, and it really requires some quality testing on your own. So with that, I hope that you are opening up the workshop worksheet at that bit link. And please don't stress if you get lost walking through the workflow. That worksheet is written to be super detailed so that you can walk through these steps at any time on your own, as far ahead in the future as you want. And we also know, because some of the steps of LandsatLinkr take a bit longer to run, we won't be able to get you through the whole workflow today. So we will be pulling some pre-baked cookies out of the oven in that final visualization stage, just to get you excited, but you'll need some time on your own to finish the workflow. With that being said, we are looking forward to hosting an office hours with all of you in maybe a month or so, once you've had time to walk through the workflow on your own for your study area and sort of catalog any issues you're having so that we can be more in depth with you and troubleshoot together. So while today is not for troubleshooting, we are hoping to do that with you and be in conversation with you as you use the tool. We can't wait to see what you do with it. So while folks are opening up the worksheet, Justin, do you have anything to add or excitement to share?
Well, thanks, Annie. You've described it wonderfully. I guess I just want to emphasize that this is not like a finished, finalized sort of product that Earth Engine team is supporting. This is a kind of a hobby side project, and it's gone through sort of many iterations. This most recent one is done in Python. Previously, when Andy and I were working on it, we did it in JavaScript, and this port to Python has just happened in the last few months. And there's been a few improvements, and things seem to work well in Andy and I's test areas. But of course, there's a lot of potential to run into problems in other places, with the availability of imagery, cloud masking, lots of other kinds of things. So, this is sort of a prototype, a place to explore MSS in a region of your interest. And I think it's super exciting. I'm just fascinated by history of landscape change. And it's fun to go back as far as you can. To me, it feels a little bit like hiking or something, like what's right around the next corner or over the next mountain. And it's fun to take the effort and time to peek around the corner. And so to me, this has been sort of that effort to look back into the past as far as we can. And the MSS data, as Annie has described, is certainly not as good as TM era and beyond. and so I have been primarily using it for visualization, and it works really well for that. And just want to caution you that using in quantitative analysis without really digging in on the composites, what is produced in the end, spend a lot of time looking at the data and understanding what it's showing you before, creating some kind of result and doing some kind of a quantitative analysis on it.
Yeah?
Yeah.
Fabulous. Okay. So I hope most of you have that worksheet up. I'm going to switch to my live demo. Awesome. Okay, the first thing I'll show you about this worksheet is that this Show Document Outline button in the upper left that looks like a bulleted list, that outline has been built to help you navigate the worksheet because it's long. It's about 10 pages. We added all those Easter eggs and details to this, so use that table of contents to click around easily if it's helpful to you. And we're going to skip all this intro stuff because you just heard me talk about it and head to step 1, set up your script. And the first step is to open that, as promised, Colab notebook. And so that link is going to take you to a GitHub, the LandsatLinkr GitHub page, and to our workshop template notebook. So the first thing you're going to do is hit that Open in Colab button that's blue, and it's right above Environment Setup. And this will now open sort of a live version of this Python notebook. So if you're not familiar with Colab, it's essentially allowing us to access a Python notebook in a browser, and it's a really easy way to get to the Earth Engine Python API. And a Python notebook, if you're not familiar, just lets us intersperse blocks of text with blocks of code, and so we've done that as well. Again, trying to write this notebook so that when you're on your own in a week or two, you remember how to go through the workflow successfully. Okay, the first thing you should do is hit File, and then save a copy in Drive. You'll be editing this notebook, we hope, so it's nice to have your own copy. I've been told that step can take a little bit of time, so while we're doing that, how many folks have used MSS imagery before or checked it out at all? You raise your hand. Nice. Okay, so you know what we're getting into today. How many folks have used Landsat Imagery before but not checked out MSS? Okay, awesome. How many people have taken a workshop with Justin this week? A lot of folks, a lot of folks. Okay, great. So now you should have your notebook saved, I hope. And we're going to hit that first step, environment setup. And if you can tell by the text block, this is kind of a complicated step. If you get hung up on it, that's okay. You can treat today as a demo if it doesn't work. So I'm going to hit run on that first code block. And to run a code block, I'm just going to hit that play button. You can also hit Control-Enter. I'm going to hit run anyway, because I hope you trust us. And this code block is going to produce a link. I'm then going to click on the link, which will open up the authentication workflow in a new tab. So on this page, if you already have a Earth Engine Cloud project, you're going to see that project populated here, and that's great. Leave it there. If you don't yet have a cloud project, you'll need to create one to access the Python API. So to do that, you would say choose project, create a new cloud project. And I think the defaults are great, but this is a permanent name, so take a moment to pick the name that you would like, and then you'll hit create. I'm not going to do that. Some of you might have administrative barriers in your account to creating a cloud project, and that's okay. We're really sorry you can't use the Python API today, but we want to troubleshoot with you in the future. So if that's you, just know you're not alone. Some folks have had that issue this week, and we're hoping we'll get past it with you, at least in office hours. Okay, I've chosen my cloud project. I'm going to hit Generate Token. We are not even halfway through this workflow to authenticate. I'm then going to choose, if you're logged into a bunch of Google accounts, choose the one that is linked to your Earth Engine account. So I'm going to choose that one. I'm going to then hit Continue. It tries to get you here. Continue is kind of hard to see. I'm then going to check these two boxes, and then hit Continue again. And then finally, this authorization code is kind of hiding at the bottom of the page. I'm going to hit Copy. And now I'm ready to close this window. Forget about it. And enter, I'm going to paste that authorization code into the open box in the code block. And I'm going to make this bigger, actually. Can you guys see the notebook okay? From right? Okay, great. All right, we know that this code block has finished running because we see that little green check to the left of the block. And we also know it's worked because it says successfully saved authorization token. What this means is that I've imported the Earth Engine Python API to this notebook, and I've also been authorized as an Earth Engine user. So great, that's probably the hardest step of this workflow. The next step is to import the LandsatLinkr library that Justin has written. So this contains all those processing functions that are handling a lot of those steps in the background. So I'm going to hit run on that cell as well.
And currently, this is just grabbing the GitHub repo. This is just sort of quick and dirty. Eventually, it might be a pip library.
Awesome. OK, we are already on step 2. So if you're in the worksheet, step 2 is still on page 4 of that worksheet. And in this step, we are identifying which MSS tile footprint we're working with. This is a key part of the LandsatLinkr workflow right now. It's working on a tile-by-tile basis to create the most accurately harmonized image collection just in that place. So if your study area is an entire country, right now this is just built to work on one tile ID and then have you composite it later. We were just chatting before this about our hopes and dreams for the future where you could define your own AOI. But for now, it's based on a tile ID. So we're going to now open up an Earth Engine script that allows us to identify where or what the tile ID is that we'll be working with. So if you're like me, you haven't memorized the entire WRS1 footprint system, and you might not know the ID of your study area. This is a script that's showing those path lines of the WRS1 global system, which the MSS sensor used. And to find your tile ID, and this is giving you a sense of their size. So maybe the whole bottom half of the SF Bay Area is one tile. And in the future, I hope you choose whichever tile ID is your area. But today, I think it's going to work best if you walk through the workflow with all of us using the same tile ID. So I'm going to click that controlled cultural burn I showed you happened over here on the coast. So I'm going to click in that area. And it does take a minute. Just click once. And two things are going to happen. The first is that the area that I clicked, it will identify any overlapping tile IDs in that place. So in this case, I picked a place where it's contained or covered by 2 different footprints. And I'm going to choose the red outlined one because that's covering more of the landmass, and that's what I'm curious about. This pop-up on the left is showing you the corresponding ID using the color, the red color is the red tile ID to differentiate which is which. And I'm going to copy or commit to memory that red tile ID. So in this case, it is 047034. OK, we don't need this script anymore. I'm going to close it. And I will paste that into the WRS1 granule parameter. So it actually already exists there. We just want to make this foolproof. But in the future, you will add your own tile IDs. So I'm walking you through it. It's got to be correct. It's very important. Don't forget to run it, because often I'll get errors later that I just didn't run a simple parameter block. OK. We're already on step 3. This is the last sort of administrative setup task of LandsatLinkr. So I know it hasn't been super fun and exciting yet, but it's about to get there right after this step. So LandsatLinkr is relying on a particular asset structure. And in order to get it to work with our Earth Engine account, we just need to do 2 quick setup steps. The first is to create a LandsatLinkr folder in your assets. And we think this is a good idea because every time you run LandsatLinkr, you're going to get a folder with each tile ID that contains some assets. So it's nice to have one LandsatLinkr folder to hold all of those tile ID folders. OK, so I've just opened the code editor. I'm also going to make it big. And I'm going to head over to the Assets tab. You can see that within that cloud project, I already have a folder called LandsatLinkr. This might not be the case for you, so you're going to hit that red New button, scroll down to Folder, and you'll see this drop-down menu. You have the option to make a folder in your legacy assets. please don't do that for today. Because we're working with the Python API, use your cloud assets folder. And I think the Earth Engine team prefers that folder moving forward. So you'll know it's your cloud project folder because it says projects at the start. And then you'll type LandsatLinkr, hopefully correctly. And you'll press OK, and it'll create a folder. Earth Engine doesn't like that in my case because I already have that folder. OK, you can go ahead and keep the code editor open. And we're going to now, because you kind of need to know where the path of this folder to enter it into the notebook. We need to tell the notebook where that folder is that you just created. So to do that, we are going to set project dir to that project directory. So right now in your template notebook, it's set to my folder, so please don't keep it there. You're going to instead replace my cloud project name with yours. And if you typed LandsatLinkr correctly, you don't have to change the rest of the path. But if you did make other changes, this is when you'll pay for that. You have to make sure the whole path matches your whole path. If you don't know what your cloud project name is, it's right here under Cloud Assets. You should be able to see it, and you should see your whole path there. And it's also up here in the upper right. OK. Once you've set that project dir variable to your path, you're going to press Run. And this function, createProjectDir, is then going to create the appropriate folder within that home directory. So in this case, it's creating a folder with our tile ID, 047034. This function does not tell you if it didn't run. So what I want you to do, once you've hit run and you see that green check, you can head back to the code editor and refresh your assets using that little cycle button at the top. And hopefully you see the folder, 047034. If you don't see it, try to get that project path exactly correct. I went through this with my sister, and she had capitalized something incorrectly. So it really is picky.
Also, just to note that there's not a lot of error message handling. If things go wrong, you might just get a generic Python error. And if you are stuck, you can submit an issue to the repository, the GitHub repository linked in this notebook. And I can try to answer it. I don't check it frequently, but that's a good place to at least alert us.
Yeah. Can I get a show of hands, like thumbs up, thumbs down, if this is going OK? OK. Wow. Incredible. OK. We are already on to step 4, and as promised, this is when it gets kind of fun. This is when your role as a spatial scientist really comes into play, and you're going to get to actually see the MSS data, which can be kind of shocking the first time. OK, the first part of step 4 is to set your imagery parameters. And if you're working through that worksheet, we are now on page 6. And again, the worksheet has a very detailed description. So LandsatLinkr takes the number of parameters to filter that MSS collection initially. You can also change the projection using the coordinate reference system variable. You can change the day of year range. So in this case, we're sort of getting a mid-year growing season range. You can change that to the whole year, 1 to 365. You'll see that that creates kind of a lot of work for you, but it gives you the most imagery to work with. The maximum cloudiness parameter is the maximum allowable percentage of cloudiness for an image. So that's that image property level cloudiness. And then the max geom RMSE is a way of controlling the maximum spatial offset between pixels. So we're going to keep those as defaults today.
And those are mostly specific to the MSS data, the max cloud, max geom. But the day of year and the coordinate reference system, those will apply to all Landsat data. And so during this process, we're building collections across the entire time series. So it'll only grab Landsat data for your day of year, and the outputs will be in the coordinate reference system. But it will retain all cloud levels and all geometry errors for post-MSS. It's working with the surface reflectance data post-MSS, so generally it's good. It's only level 1, or tier 1. Whatever the best surface reflectance product there is what it's working with, so we just sort of trust it.
Yeah, I can't keep track of all the 1s and 2s. OK, Great. This next set of parameters, LT params, these are the parameters for running LandTrendr in that final step as we promised. And so we're going to keep these as defaults today. Again, if you dive deep into LandTrendr, which we hope you do, this is where you would control how that's running in that final step. The one that we want to highlight is FTV bands. This parameter is going to control which 3 bands you can visualize in that gorgeous animation in that final step, and so you can play with that on your own. We chose red, green, blue because the true color imagery is very familiar to all of us, but probably for your analysis, you'll include some other bands. This last parameter, LLR params, is the LandsatLinkr specific parameters, and you can see we're plugging in a lot of the parameters that we've already defined, including those LandTrendr parameters. So nothing to change here, but please remember to run this block. I usually forget and get an error, so we're just setting all these parameters, binding them to their names. And now we're on to the hard part. This function, viewWRS1 call, is going to take all those parameters that we just decided on and print out all of the matching thumbnails for all the MSS images that correspond to those filters. So go ahead and hit run. This is going to take a little bit of time. These are real MSS images for this area. So you can see it's kind of, some of them look great, some of them have lots of clouds masked out already, some of them have wild scanline issues. So this is when we're going to get down to the work and really have to be hands-on with the data and decide which images we want to include or exclude. Okay. When we get that green check, we know it's done running. I'm going to scroll to the top and talk you through the workflow of how to exclude images that look terrible to you. Just in case you're getting nervous, we have already created a list here just below it of the image IDs that we'd like to exclude, and this shows you what the finished product looks like. But we think this step is really important, so we want to try to transmit sort of a sense of how to decide which images to include. So we'll go through a couple years together. But just know that there's no pressure. You don't have to get through all the images today. So I'll walk you through what it looks like to create that exclude IDs parameter. It's a list of strings, and the strings each correspond to the image IDs of the images that you do not want to include. So in this case, this is off the bat a pretty easy decision to make. This image has huge scanline issues. Over half of it is missing data, so we definitely don't want to include it. So I would copy that image ID, head up to exclude IDs, and put that image ID between quotes. I'm going to add a comma to the end of the line, so I just keep adding to my list as I go through. OK, this next image, also from 1972, doesn't look perfect. You can see there are those thin, hazy clouds. I should say, I did forget to say, LandsatLinkr is built to deal with some scanline issues and really thick, puffy clouds, but it's not able to filter out really thin haze, and it doesn't do a great job with like huge scanline issues like we saw with this image. You should exclude those from the algorithm. Do you have anything to add on that?
Well, just actually in the first one,
yeah.
It's probably OK. I mean, it's missing lots of lines, but they don't look like they are like errors. So if you only had a single image, if this was your only image in 1972 and you wanted to have a look, you might include this. You just wouldn't have full coverage for the scene. But as Annie said, there's more in 1972 that have full coverage and that look decent. So you might just exclude that first one and rely on a better 1972 image.
Exactly. That's what our process generally looks like. We'll look at all of the images for a given year and decide what are the best 1 or 2 images. If you only have one, that's enough. Don't include a pretty bad image just to have more images for that year. So in this case, I'm not sure about this image. My study area is on the coast, which looks like is kind of hazy. But if I scroll down, this is what Justin means when he's saying, scanline issues that look like errors. This colorization is off. It's not missing data, it's like bad data. So knowing that and knowing that there are no more images for 1972, and I definitely want to exclude this one, I will copy that. And I've decided this is the one I want to include for that year. So that, I'll add a new line, pop that image ID between single quotes, and I would go through the rest. You'll notice that this tile ID does not have data for 1973 in our day of year range and with our cloudiness parameters. And that might be the case. 1983 is kind of a funny year. So if that happens to you, LandsatLinkr is going to create a, what's it called, filler image?
Yeah, filler image, dummy
and
image.
yeah, just dummy image. And when it's run through LandTrendr in that final step, it will be interpolated using the years around it. So this won't look like missing data in that final LandTrendr output, but we know that, that for 1983, we don't have data. And it's important to just keep track of that. Yeah.
Yeah.
And so again, this image I would exclude. We've got scanline issues, missing data, and what looks like erroneous data. And my whole study area is missing because of cloud cover. This looks fabulous. So this might be the one I choose for 1974. I want to show you some other examples of colorization looking off. So even if we didn't have these scanline issues in the background, you can see that this image is colored differently. It's a little bit too green compared to the others in the series. So this type of major colorization difference is another reason you'd want to exclude that image. Anything to add there?
Totally.
Or, yeah.
And again, if you only had a single image for that year and it was discolored a little bit, one of the processes that it goes through is to be normalized to a reference image from the 1980s era of MSS. And during that process, this discolorization can be fixed. But if you have better images, it's nice to exclude these.
Yeah, that's a great point. LandsatLinkr is working hard. These data are not perfect, so there's a lot happening behind the scenes to try to make this pseudo TM imagery. Okay, so I'm going to uncomment all of this, and I've already run this cell and run this function. We've gone through it together. This step can take quite a bit of time, especially if you're looking at a lot of years or a lot of days of the year. But it's probably the most important step. And I think I've said that about every step. But I'm going to run this code block that assigns all of our list of excluded IDs to that parameter and then adds that to our LLR params dictionary. OK. So now we're on to step 5. This is when we start getting into some of the more heavy processing steps. And so in this case, every step of LandsatLinkr depends on the previous one. So we're exporting assets, intermediate assets along the way, and each next step depends on the one before having been run successfully. So this is when we don't have time because these processing steps are serious. As you can imagine, there's a lot of work happening behind the scenes. So we encourage you to just keep running the steps in the background as the tasks finish, and I'll show you what that looks like. But we are mostly just going to be talking through what these steps are doing. We don't have time to have everyone complete every task, just because it's a lot of time, a lot of work. OK, so Justin just mentioned that reference image. This reference image that we're creating is going to help us harmonize within the MSS time series. So within those 12 years, we'd like the imagery to be harmonized to each other at the very first step. So to do that, you're going to run this code block. And what this block is doing is running the export MSS ref image function using our parameters and then starting a task in your Earth Engine account to export that reference image. So if I head over to my code editor, you can see I've got a lot of failed tasks. But that task is now running. And this task will fail because that asset already exists in my in that tile ID folder. And so you'll see this fail in a few seconds, but you can keep track of the tasks either in your task tab in the code editor, or this should quickly print out the words failed in all caps below the code block. If it runs for you successfully, which it might in about 10 minutes, it'll print completed, and you'll see that green check next to the code block. So that's how you know to keep going once that task has completed. So now that we've created that reference image, that next step is to harmonize the MSS time series to that reference image. So as Justin was saying, that miscolored 1974 image, 1974 image would be harmonized using that reference image in this step. So you can see it failed. Hopefully for you, it says completed at some point in the next 10 minutes. This step also takes some time. It takes between 10 and 25 minutes, and it's going to export another task. this task is going to create that harmonized MSS time series. And so that you can find here. I think this is the right one. OK, so this is actually saved as an image in my assets. And each year and band is saved as a band in the asset. So you're always welcome to play with your gorgeous MSS time series by itself. You don't necessarily have to take that full 50-year view. This on its own is an awesome asset, I think.
And maybe just real quick, what it's actually doing there, for each MSS image, it is subtracted against, it's compared against the reference image to find pixels that have not changed very much. And then it pulls out a point sample from both the reference and the image it's working on, and then does random forest regression, just to make them line up with each other a little bit better.
And you'll see random forest come up again when we harmonize with the TM imagery. Yeah. OK. So this is when we're just hand-waving and walking through what the tasks do while you guys are hopefully trying to get them running in the background, one by one. So step 6, we are almost through the processing at this point. This is when we take that harmonized MSS time series and harmonize it with the TM imagery. So this is where a lot of the magic is happening, and a lot of the work that Justin's done really gets to shine. This is going to create this first function, export MSS to TM coef call. This is creating a aggregated sample of points between those coincident image pairs that we mentioned earlier. And so it's going to take those points, pull out values for each image pair, and export a table. That table is then what's run to train a random forest regression model to then create that pseudo-TM imagery for all the pixels across all years. So I don't know how well I described that. I'm hoping you can pop in. But once that task runs, and you can see that's this failed task over here, but I already did successfully run it some day long ago, and this is what that looks like. Do you want to add anything?
Just that these images, well, I guess that's the sample.
Yeah, this is a sample still, yeah. So these are sampled values that will then train a model. Pretty fun.
The two MSS image stacks that come out as assets are a huge stack of images. So to make the export efficient, to just do it in one export, all images for the MSS era are just concatenated as a bunch of bands. So if you're looking at that, it has 100+ bands probably.
I'm curious.
Yeah.
Wow.
Almost. And processes later on that use this, just decompose it. Just FYI.
Great, OK. So we've created that table with our sampled values, and now we're going to use that to build a model and then harmonize our MSS imagery to TM. So we're creating that pseudo-TM imagery in this step. This is really exciting. Oh, sorry, I got ahead of myself. We are first going to export an MSS offset image. If you remember from those slides, those two lines of MSS time series and the TM time series and how they were sort of like brought up to match each other better, that's essentially what the offset step is doing. Is that right?
Yeah, so when you draw your point sample to do the random forest regression between the MSS and TM, to predict TM from the MSS, that regression line is sort of the mean of your data cloud, but you've got points that are real dark and real light that don't quite fit that mean real well. And so we do this point level offset for all of the coincident images for TM and MSS at the pixel level. We gather them up per pixel and figure out what the difference is. And it generally, for light and dark pixels, an offset correction really helps. So we've already applied, we've predicted TM from MSS, and then this is just an extra step to kind of help out dark and light pixels to get a little bit more aligned and reduce that stair-step function if there happens to be any left over.
And this, I hope you're getting a sense of how hard Justin has worked on this, tweaking every step and adding these additional steps so that LandsatLinkr looks really good. So this is a ton of work and scientific thought behind these really simple functions. Okay, so you've exported that MSS offset image, and I know you haven't done that yet. I'm sorry that you're far behind in the tasks. I have a big advantage on you all, and I ran these beforehand. But this final step, this is really exciting. It's very understated. Function name, export final corrected MSS collection. So this is creating that pseudo TM collection from all the work you've done. And when you run that, you're going to get, again, sort of an image collection that's compressed into one image called WRS1 to TM stack. And this is also going to have a ton of bands. And you can see for each year and for each band included in our imagery, we have, and it's predicting the other, like, here we have SWR. You'll notice that's not an MSS band. So this is sort of synthesized and modeled based on all the work we've done so far. So you've got all your years, all your bands. This is really exciting. This is that pseudo TM imagery. You could run with this. You don't have to run through LandTrendr or link it to the 50-year archive fully, but we're going to do that. It's pretty exciting. Okay. So you'll see you've made it almost to the end of the notebook workflow. This last step is to take that pseudo TM imagery and link it with the rest of the archive and run that all through LandTrendr to create that temporal segmentation. So that was that linear, fitting those spectral values each year to linear piecewise functions that are a lot cleaner, they're filtering out some noise, and they're also a lot easier to interpret. So we're able to get these clean time series that are capturing big annual changes or regrowth over time, those kinds of ecological or landscape changes generally. So to run this takes a long time. I think it took me 2 hours to run. But that is going to create one final asset called LandTrendr. If you're familiar with LandTrendr, the outputs can be a little black boxy and hard to work with. So we're going to head to the code editor next with a workshop script to show you how we've worked with it, just to give you a sense. But this is an asset with it's an image with only 5 bands. So you might be wondering, how can that be? And we'll show you how to decompose, as you say, and work with this output, because it's extremely powerful. This is our highly fitted, harmonized 50-year time series captured in this one image. Okay. Did you want to add something?
Just that LandTrendr is run, it's doing the segmentation on NDVI. And we've selected NDVI because it can be calculated with both MSS and TM type data natively. And so it seemed like the best index to be segmenting on. It's the one that would probably have the least kind of stair step if there happens to be any left over.
Yeah, and that we're limited again because if you remember, MSS only has those 4 bands, and NDVI makes use of the red near infrared that we do have. Great. Okay. In this final step, step 8, imagine you've run your whole workflow, you've got that LandTrendr asset in your tile ID folder, and you're ready to use it and work with it. You're going to open up this example script at the end of the notebook. If you're in the worksheet, it's also step 8, and it's also linked there. Okay, so for me, this script is one I've written, and so it's in my owner folder. But when you click that link, you should see it pop up in your reader folder. And you'll see a repo called users, analyses Taylor, and then G4G with one script in it, and that's the script we're going to use today. You can hit run. I'm going to talk through what some of this is doing. I think it's really helpful. As a longtime Earth Engine user, I really love chatting about the require function. This is a way to essentially import someone's scripts into your own. It's much like importing a package or module in other programming environments, and we're naming that LLR. So we're able to call any functions that Justin has written in his module or script repo. We can call those directly using LLR dot and then the function name. So that's really useful. The other key part of this script is that we're importing that LandTrendr asset. So when you run this on your own, you will change this file path to include your cloud project and your tile ID. Okay. So let's look at what it's doing before we look at these awesome outputs. You can see you can control which years you're viewing. RGB bands is showing you which bands would you like to visualize in the red, green, and blue channels. As promised, we used those red, green, and blue bands because we wanted to see it in true color. But this should correspond to that FTV bands parameter back in maybe step 3 when we were setting the LandTrendr parameters. And it's okay if that didn't make sense. I'm sorry about that. Here are our visualization parameters, how we want to look at the true color imagery, and then how we want to export it as an animation. You can play with those and add many more parameters. And then this is the meat of the script. Essentially, the most important thing we have to do when we've imported that LandTrendr image is to check for issues. And there might be. There will probably be issues. It's MSS data, so we have to be really careful and comb through the data and make sure it's showing changes that make sense to us, maybe based on your experience in a study area or study system. So to do that, it can be hard to check every single time series for every single pixel in your study area. We don't expect you to do that. What we've done is created a change image where 3 years are represented in the red, green, and blue channels. And so this is helping, this is much like that slide I showed you of Mount St. Helens, where areas in color are highlighting areas of change between 3 years in our time series. So in this case, we're looking at 72, 77, 82, and we're just taking the green band to compare. You could choose any band or any years and play with this. But this gives you a sense of like, okay, these areas have cropland, so I feel comfortable that they might have changed. That makes sense to me. Maybe there's some logging happening in these redwoods. Maybe there's development here. I can see the salt flats changing a bit, and the levees over here changing. I can see changes in the Central Valley with crop rotations. So overall, I feel comfortable. But this visualization might show you something that you don't think is quite right. And the way to check that is to activate the inspector tool up in the upper right of the code editor, and click on a pixel of either change or no change where you're like, that's not quite right. You're then going to, you'll see we've added the full Landsat collection as an image collection to the map. We're not visualizing it here, but if you expand series, you'll see the time series for that chart. And this should be fitted. You'll see that linear effect from LandTrendr. So something serious happened in 1979 in this area. I'm not familiar with this area, I don't know what happened. But this is how you would check the time series of individual pixels or really get fine-grained in your study area to look for issues. And if you see an issue, that's okay. You will have to go back. Maybe the year, maybe I don't think something happened in 1974. So if you remember, I'd go back to step 4 and print out all my thumbnails, and I'd say, okay, I need maybe a different image for that year. So there's an issue being caused by the image I chose. Or maybe you want to exclude some images that you did include. Maybe there are no images that are good for 1974, so what you might do is increase your day of year range until you get some that look okay. So those are all sort of workflows to go through when you find issues in your time series. And I'm really just looking for those first 12 years of my time series for issues. If you have issues beyond that, that's okay. That's just a different workflow to fix it up. And to note that if you do want to rerun with different images included, make sure to delete the assets that you have in that LandsatLinkr folder. These all need to be remade based on those included images, and Earth Engine will fail your tasks if they already exist. So you do have to put in some time deleting those. Okay, so that's how you would sort of spot check your time series for your study area. And as promised, LandsatLinkr creates these beautiful visualizations. And so we've also written this script to create and print that animated thumbnail GIF, which you can then save as a GIF just by right-clicking on it. And so that's the output, that highly fitted, harmonized 50-year view of a tile ID of a study area. And we cannot wait to see what you do with it and talk with you in office hours. And I think now I want you to have time to add anything, and I'm just going to scroll through the worksheet and see if I forgot anything fun to say.
Sure. I mean, and he was talking about looking for errors, and probably the most common one is cloud contamination. So there's a cloud masking algorithm that gets applied to the MSS imagery, but MSS imagery, at least from 1, 2, and 3 Landsat, only has 6-bit data with 4 bands, and 3 of them are really correlated. So there's just not a lot of information to try to separate cloud from other bright surfaces. It does pretty well with thick clouds that are really opaque to being able to see through to the surface. But if it's thin clouds, generally Landsat or the MSS mask won't pick it up, and you will see that as maybe a spike in the time series when you're looking through a profile, and it would maybe look like a blob of like reddish, pinkish color when you're inspecting on the map. There's a few things in the LandTrendr parameters that you can set to try to get rid of that. There's a despiking parameter that can help you eliminate spikes from clouds. You can also, we've set 10 segments, which is actually kind of a lot. And one of the pixels Annie clicked on, you could notice had a lot of kind of fuzz at the beginning of the time series. You could set max segments to something lower. Yeah, some of this just takes some trial and error, understanding how LandTrendr is fitting in your region. And there's actually a guide, I think it's linked probably to a package to help you understand Landsat LandTrendr a little bit better and how to set those parameters. And also any of the outputs, the LandTrendr outputs can be run through any of the functions in here. So once you have the LandTrendr outputs, you can go to this package to work with them more.
Great.
Yeah, any questions about MSS, LandsatLinkr, or LandTrendr?
Anyone already know how they're going to use this? Can't wait to tell everyone. Oh, great.
I was interested about the harmonization, particularly with the missing blue band, and if you've compared the random forest model between different tiles. Like, does it vary much between tiles, the harmonization model?
I've not compared, but I've thought that you could probably generate a global model pretty well, just given that there's not a lot of information in the MSS data, not a lot of variability, that you could probably fit a model pretty well, maybe by sampling a few different environments. And I think, yeah, we were talking about this earlier, that working on a single tile is kind of not the way of the world now. We should be able to just kind of draw a region around all of California and say, give me outputs for California. And so I've been thinking of ways that we could sort of develop a more representative model of larger regions, but I've not compared region to region to see if they change a lot, how different they are. Certainly something I'm interested in to make this process easier, if we could establish sort of a global model that worked well enough.
Hi.
Hi, Annie. Hi, Justin. And just to say, maybe less of a question, but just say that per Annie's question about like what people are planning to do with this, at Severe we've tested out LandTrendr quite a bit, and part of the promise that we see with this, in addition to in theory being able to generate 12 years of additional data from the MSS stuff, one of the things that at least I'm interested in looking at is how we might then take this, for instance, and look at like Belize and see if we can kind of go back in the deforestation history again, some of the stuff that like Annie's showing for California. So again, just to say, congratulations on the really great work that y'all are doing, and we'll definitely be testing it out and getting back to you about office hours, et cetera. So thank you again.
Thanks, Emil.
Great.
Yeah, we'll look forward to hearing how it goes.
Yeah, can't wait
Fingers
to try.
crossed.
Yeah, I'd like to reiterate, thank you so much. It looks like a lot of work. I just wanted to ask if there was any way we could interrogate that. I see you had a map on the slide with the number of MSS tiles around the world, and it would be really useful just to zoom around to see, is it even worth trying something in this area? And it would be even better if it was a count of cloud-free pixels instead of a scene count. So that's just one question. And the second, I was just looking at your JavaScript module, and I noticed some assets weren't shared. I'm not sure if that was intentional or not, but just giving
Mine or
up.
Annie's?
I think they were yours. Yeah, I'm pretty sure they were yours. But yeah.
We can look at that. Yeah.
Yeah.
That's a great idea. And that That slide is actually a screenshot of a web map, at least, of MSS coverage, so you can zoom around, but I'm not remembering the link. It's a USGS web map.
Yeah, I think you linked to it in the slide, and that will take you there.
Oh, okay.
Probably.
I hope I did. Yeah.
And there's lots of functionality to zoom in on a year, a type, the sensor, the product level, but it won't tell you about cloud-free pixels. I've thought about that too to generate a composite. Running the MSS cloud masking is an expensive task, sort of. Yeah, so I haven't done it, but I've thought also that it would be nice to just have a map of like, here are the clear pixels.
Yeah, but that scene count sounds very useful, a useful starting point anyway.
Yeah. I thought it'd be cool, we have the Earth time lapse that has the Landsat from TM onward. I thought it'd be cool to try to do this globally and include that, the MSS years in the Earth time series. But looking at that map, it doesn't seem like it's feasible enough everywhere to sort of bring it into a product like Earth.
Anyway, thank you.
Yeah.
I'll just say one last plug. Maybe you don't care about the 70s. They still contain really important historical context for present-day landscape conditions. So there are 2 LandsatLinkr papers that we cite in that worksheet, and one of them uses those historical conditions to generate results about the present day in terms of how tree structure, forest structure has changed over time. So it's cool for everyone, I think, yeah. But I think we're at time. So thank you all so much. This was a joy to get to share with you, and we're really excited to be in conversation, and we'll be reaching out about office hours via the G4G Google group, and then also via the developers group so that we get all our folks joining online as well. So thank you so much.
Thanks.